Welcome to the next lecture of mechanics of material. So, next topic we are going to discuss about thin cylinders. So, what is thin cylinders is nothing but the shafts or the cylinders whose L by D ratio is L by D ratio is less than or equal to 1 by 15 or 1 by 20. Okay. 1 by 20, this is diameter internal, not external, the diameter internal. So, the ratio of the internal diameter to external diameter ranges from 1 by 15 to 1 by 20, then those are called as thin cylinders. So, why we are much bothered about thin cylinders is nothing but, so for example, if you take a thin cylinder which is carrying a fluid inside, so let us take this as a cylinder, thin cylinder which is having a fluid inside. So, that fluid will try to apply the pressure, internal pressure in all the directions on the walls of the fluid, on the walls of the cylinder. Okay. So, because of this pressure, so it will have a stresses generated in the inside the surface. Okay. This is fluid which is present inside. So, because of this, it will create some pressure on it. So, what with that pressure, what are the various types of stresses generated with the pressure? What are the types of stresses generated in the material? Okay. So, this is the internal diameter which we generally represent as D, and this is the thickness of the material. So, generally this is the thickness. And another thing is the thickness will not be present on the surface, but for say namesake I have drawn this. So, here it will not be there. Obviously, if this is a cylinder, we will see this is a flat surface. So, this is your, here it will, the pressures will be acting. Okay. Same way here also, clear. So, on this surface, there will be pressures acting. To show that surface itself I have drawn this, but whereas there will be no surface at the both the ends, this front end and cross sectional area will not have any kind of thickness. So, these are the two thicknesses which we generally see in a pipe. Okay. So, what are the types of stresses generated in this? So, generally in on thin cylinders we will be coming across two type of stresses. The very first stress is circumferential stress, which acts along the circumference. This is also called as Hoops stress. Another is longitudinal stress. One is hoop stress, second one is longitudinal stress. So, first of all, let us see what is this hoop stress, then we will go for longitudinal stress, and we will get some formulas for circumferential stress, hoop stress, that is nothing but circumferential stress. So, let us consider a cylindrical element which is cut along the circumference of the circle, like this is your cylindrical cylinder which you are having. So, I will cut at this section. So, I will cut along the axis like this. I am cutting this part. So, the fluid is present below this, above this, correct? So, below this, above this, below this, above this. Now, below this, here if you see, so we will draw this here again, clear. So, if you see this, this will appear like this. When you, after cutting, it will appear like this. Okay. So, but whereas lower half you will observe like this, correct. So, this is your lower half. So, in this way you will observe. So, when you cut in this part, so because of the internal pressure, this area will experience some kind of stresses which tries to oppose, okay. So if you cut that surface, you can able to see, I think, if you cut this surface, that surface will be like this. So this surface generally will have a stress acting along this length, okay. Now this pressure will be acting on this whole plane. If you cut that plane, the whole internal pressure will be acting. So these two pressures, since the fluid is under equilibrium, so the pressure acting on the axis, you can take pressure acting in the axis will have a pressure force. Because of that pressure acting on the axis, we will be having a pressure force, that is force due to pressure is equal to pressure, internal pressure Pi, we write generally Pi, into, now see on which area it is acting. So the pressure is acting on this area, this is your diameter on this whole surface, and this is acting for a length of L meters. So the pressure is acting on a length of L into diameter d. So L into d. So pressure Pi into d. Now this force due to stresses circumferential. So that we generally take it as sigma I, you can take sigma t, you can take circumferential. Sigma 1 I generally take sigma 1. So this is the sigma 1 which is acting on the surface. So this on this surface it is acting, correct. This surface, what will be the area of this surface? This is your length, okay, this is your thickness, thickness, length, okay. So it is having for two surfaces. So this is also L into T, this is also L into T. So on two areas it is acting. So sigma 1 into 2 into LT, right, 2 into LT, on two surfaces it is acting. So these two forces should be under equilibrium. Then P1 into L into D should be equal to sigma 1 into 2 into L into T. Correct? This L cancel. So sigma 1 is equal to Pi D divided by T, 2T. So this 2 also will come here. So this stress value is nothing but called as Hooke's stress or circumferential stress. Hooke's stress or circumferential stress. Okay, till here any doubts? So if you have any doubts, please you can ask me in your comment section. Next is longitudinal. Generally the derivation most of the time they will not ask, but however for safety purpose I am solving this. So most of the time you need to remember the formulas. So next is longitudinal stress. So how to calculate the longitudinal stress? Now the same surface, the same cylinder, if you see, what is longitudinal is along the axis. This is your longitudinal, this is your longitudinal. If this is your circular section, so this is your longitudinal. Circumference means along this, okay. Now this is your longitudinal axis on which your load is acting like this. That is nothing but stresses are acting like this. Stresses are acting from here because of the internal pressure, okay. the stresses are acting like this along this whole surface, they will be acting. So, these are your longitudinal stress, which we generally represented as sigma 2, but whereas your internal pressure, if this is your pipe, so on the pipe at the faces you will be having pressure acting like this. So, for longitudinal, if you want to show, so generally show as this. So, this is your circumferential on circumference, okay, clear. So, this is for your, so these are your internal pressure, this is a Pi on the surface, okay. So, by water flowing inside, water flowing outside, we will try to apply the pressure on both the sides, okay, clear. So, this pressure force is equal to P internal into, it is acting on this area, it is acting on this area, correct. So, this is your area, it will be acting on the whole surface like this, pressure, okay. That is pressure force is equal to P into pi by 4 of d square, P into pi by 4 of d square. Similarly, resistive force are force due to stress is equal to sigma 2 into, now see sigma 2 is acting on this. So, this is your, if you cut this from here, it will appear like this. Why means only on this part, only on this part, here again it will not be act. So, only in where the material is present, only at that part only the stresses will act. So, for that reason we will take that area as, so this is your 2 pi r, okay. Internal surfaces, this is your internal surface, this is your T. So, the area of this is 2 pi r into T, that is equal to pi d into T, you can take anything. So, I will take it as pi d into T, okay, pi d into T. Now, these two forces should be equal, that is Pi into pi by 4 d square should be equal to capital D, capital D. So, once you use, all the notations should be same, do not get confused. Generally, we keep on writing the formula pi by 4 d square. So, I have done that mistake. So, this d gets cancelled. So, sigma 2 will become this pi cancel, Pi d divided by 4t. So, if you see that sigma 1 was P d divided by P capital D divided by 2t, sigma 2 is P d divided by 4t. Since denominator is greater, sigma will be greater than sigma 2. So, this makes hoop stress an important topic to study. This makes, so these are the stresses because of which the material may get fail. So, we concentrate more on hoop stress comparing to that of longitudinal stresses. This is the reason. Okay. Now, there is also another stress which is called as shear stress, So, what is this shear stress is nothing but it is the difference of both this, the difference of sigma 1 sigma 2, that is P capital D divided by 2t minus P d divided by 4t whole divided by 2. Okay. When you take the LCM, this will become, both should have the same sign, 2 P d minus P d divided by 4t whole divided by 2, because I have to take the LCM. This is 2 4. So, this will become PD divided by 8t. So, shear stress tau is equal to PD divided by 8t. So, in this way we are having three values. One is pi 1 is equal to PD by 2t, pi 2 is equal to PD by 4t, another is PD divided by 8t. So, basing on these three formulas, you will be regularly getting problems. You will be getting most of the time few problems. Let us take a small problem and then we can because this is not the much important topic compared to that of your shear force and bending moment diagram. I will solve only basic two problems, then we can wind up this also. So, the question has been given like this: a cylinder of internal diameter 2.5. So, the internal diameter has been given as 2.5. Okay. So, this is also, this is in meters, this is in centimeters. So, and the thickness of it, so thickness is this. So, this thickness has been given as 5 centimeter. So, let us write the data. Di internal is equal to 2.5 meter. Since this is should be converted into mm, because your internal pressure is your stresses will be in mm. So, 2500 mm. Next is your thickness T is equal to 5 centimeter, 50 mm, correct. So, then your sigma max is given as 80 Newton per mm square. So, sigma max is nothing but Hoops stress. Why? Just now I have told that Hoops is the maximum value because its denominator is lesser one. So, sigma 1. So, that is equal to sigma 1 is equal to PD divided by 2t, that is P into diameter is 2500 divided by 2 into 50, but whereas the maximum value is given as 80, correct. That will become so P is equal to 80 divided by 25. So, this will become 3.2 Newton per mm square. So, the internal pressure is 3.2 Newton per mm square. In this way, we will try to solve. Okay. So,